Hi everyone, my name is Ryan Beisner. I'm a engineering manager with NVIDIA, and welcome to Day on Kubernetes. I'm excited to tell you a story about a project that my team has worked on over the last year or so. It's a quick story about a write-through object cache that my team put in place to accelerate object data access on fleets of global edge Kubernetes clusters. It's a pretty short session, so I want to keep things moving right along. We could easily do a deep dive for an hour or more on this thing. Just so you know what to expect, I'll first talk a bit about the environment in which we operate, what we have, what we need. Then we'll clarify the challenges and constraints, and to identify what we're working toward. And followed by that, we'll look at the solution, how we decided to meet these requirements. And I also want to touch on some alternatives that we considered throughout our assessment process. A lot of different options out there that could suit this particular use case. I want to leave a few minutes at the end for Q&A if possible. So let's get started. So what do we have? The first use case for this write-through object storage cache is cloud gaming. NVIDIA's GeForce Now provides a way to achieve fast frame rates at a high resolution, streaming directly from GeForce RTX GPUs with real-time ray tracing with RTX on, maxed out graphic settings, basically providing a desktop gaming experience in the cloud without having to build a fancy home high-end gaming PC. So that's one of our primary use cases for this. Inferencing and generative AI workloads are other use cases where we're working toward implementing an object storage cache such as this. The NVIDIA inference microservice and cloud functions are services that have data transit patterns that also would be benefited from such a cache. So NIM is the NVIDIA inference microservice. It's basically an optimized cloud-native microservice that's designed to shorten the development time and time to market, basically making it so you can deploy your generative AI models across the cloud, in data centers, and pretty much anywhere you've got GPU-accelerated systems. So I'd like to talk a bit about the scale of this. The scale is planet Earth, of course. And so for several years, my team and my adjacent teams have been working to build this, and we've actually operated for many years, operating this Kubernetes on the edge at global scale. The system as a whole is comprised of tens of thousands of GPUs and smart NICs, which are key components to delivering low latency streaming and a desktop gaming experience for thousands of game titles across the world. So we serve millions of user sessions worldwide, and we've learned a ton throughout this, as you can imagine. There's a lot of Kubernetes there. Let's talk about some of the challenges that we were faced with. Aside from the scale, user mobility and locality is one of the specific challenges. In other words, users happen to have different patterns of movement. Maybe some are more static to a certain metro area. Others may travel the world, such as you and I. So that introduces a data locality and a latency challenge that's a natural coupling to these. And so, for example, some regions, more remote areas of the world may have higher latency to public cloud providers. System capacity is one of the challenges. We want to always make sure that we're maximizing the utilization of our systems. And of course, we all need to be mindful of the potential surprises when dealing with the very real costs of handling object data egress at this type of scale. So here we have basically a classic triple constraint scenario where we want to continually improve the user experience. We want to continually manage and monitor and maximize our capacity, and of course optimizing around cost, if possible reducing cost. And so no pressure on the team at all. We targeted all three of these. So translating these challenges to goals, it's pretty natural. We want to maintain the high level of convenience that our users are accustomed to in accessing their cloud platform. Regarding user mobility, the idea is to provide that seamless, consistent experience, and in terms of performance, faster data load and faster data saving times were some of our goals, and we want to, of course, optimize around cost along with the additional security model requirements that a cache might introduce. So impacts are the measurable things. What are we aiming for? What do we want to achieve? So the non-negotiable in this is the user experience baseline, and that is being that it just works anywhere. That's the whole experience, is that this system just works from wherever you are. Could be from your laptop, maybe it's from some mobile device that's sort of a, not a gaming machine, but then you can get that full experience as a result of this GPU cloud. So by holding that line and by achieving these other goals, we anticipated a notable and measurable improvement in terms of session launch time, and also in terms of the time it takes to free up those system resources following your session to free them up for the next user. And of course, along the way, the bottom line has to be met for operating a cost-efficient product and probably most importantly, a trusted product. So leading into the solution, I want to talk about some of the open source components that we use. Naturally, we're here at KubeCon. We're using Kubernetes. We use Kubernetes and KubeVirt for container and virtual machine orchestration. And at the core of the network, we use OVN for the software-defined network. Multis CNI is also in the mix for some of our multi-homed pod networking needs. And Metallb is an interesting piece here. It's what we use to expose some services outside of a Kubernetes cluster to some of our neighboring Kubernetes clusters. Also pretty much a commonplace in today's Kubernetes world. We used a fairly recent oven Kubernetes implementation called egress IP, which provides custom SNAT routing, essentially as the counterpart to Metallb on the ingress side. So like many of you, we also use Prometheus, Grafana, Flux, and Helm for our observability monitoring, GitOps, and deployment automation. So that all sounds probably pretty familiar. But at the core of this particular solution, what we selected is a project called AIStore. So a lot of good communities involved here. I would be remiss to not shout out to say thanks to everybody that's involved in all of those things. Awesome stuff. So real quick, I want to talk about AIStore. I'm not going to do a deep dive on it here. There was a session at KubeCon North America, and I'll link the YouTube link at the end of the deck. But essentially, it's a lightweight object storage system that's tailored for deep learning AI applications and for our case, a distributed file cache. It supports a lot of different S3 backends, such as AWS, GCP, Azure, Oracle OCI, and other AIStore clusters. It's got a support for generic S3 clients and also a native Go API. This is an open source project, started in 2017, released with an MIT license from NVIDIA. So it's actively developed. Traditionally, this AIStore has grown in scope to include a bunch of things that we didn't necessarily use in this use case, things like ETL offload, distributed shuffle, batch training, sharding, a lot of things that are useful to train deep learning models on a petascale data sets. And so in our use case, we simply use AIStore in a write-through cache configuration. So there are a lot of features that it will do that we don't necessarily dive into. At its core, you've got really two components, the AIS proxies, which are not in the data path. They're the initial connection point from the clients to let the client know which target to hit for the particular object that it's requesting. We also have an operator to make this pretty seamless in Kubernetes. So to bring AIStore into the Kubernetes cluster, we use as I mentioned, the AIS operator to control the life cycle of the AIStore proxies and the storage targets. These, by the way, are deployed as daemon sets. Each of the targets essentially represent the back-end storage, and in this case, these are local NVMe disks presented through a PVC. So pretty common abstractions for the Kubernetes world. And with overlay networks, network policies, Metallb, OVN, Oven Kubernetes, egress IP, as I mentioned, we're able to construct the necessary logical networks and the logical routers to make this system work across our existing estate. So this was a pretty impactful single cluster proof of concept that achieved, essentially our proof of life for the project. So extending that, now I've this is the simplified network diagram. I've tried to condense and simplify quite a bit. You've got 4 Kubernetes clusters on the screen here, one of them being the host of the object cache. And so there are some assumptions that we're making here, and I'll tell you about that. Wherever we have our own private network infrastructure, we're able to empower these workloads across adjacent edge clusters to leverage this regional write-through cache without having to traverse the internet to retrieve these objects. So each pod is represented by one or more VFs on Bluefield and ConnectX smart NICs. That provides line rate network offload acceleration. You can see that we have east-west overlay networks in each of the clusters. That's essentially for the pod-to-pod network traffic within the cluster. There are actually, in reality, a lot of different overlay networks in the system, but again, simplified here for the visual side of things. The AIStore proxy and target pods are multi-homed with one network attached to the east-west overlay, the other NIC attached to the north-south side of things through Metallb and the oven egress IP to make that service accessible from those neighboring clusters. So we also have certain networks that are encapsulated across the underlay via VTEPs, and this is what's necessary in order for us to get the granularity that we need to provide access control, to do the traffic segregation that's needed in this case, and essentially apply network policies for our security story. So an important distinction here is, although AIStore can be quite resilient depending on how you deploy it, we view this cache as opportunistic. And that means that it's not a single point of failure. The cache clients will simply fall back to the origin, the source of truth, in the event of a missing object or an expired object, or in the event of some sort of system outage. So it's not in the failure path, and that was part of our requirement in this. So let's say, for example, this is London. Let's say we have several data centers in London. You've got workloads running on clusters 1, 2, 3, or 4. I guess we've got 4 here. In this picture. So workloads running on any of these have a mutual cache, and they have shared private network infrastructure, which means that subsequent calls to these revisited users within that geography can benefit by having this cache available, and again, not reach out to the internet to pull across gigabytes and gigabytes of data, perhaps. Okay. Now, if we apply that principle back to this picture and deploy regional caches on a global scale, you can see how powerful this could be and just how much impact it might have. As a side note, I'll point out here, this is a good opportunity to visually describe why the write-through cache is the model for this. So this cache is essentially a write once, read once, or read never cache. Every time a session comes through, we assume that data is modified, therefore that cache object is effectively invalidated for the next session. And so let's say you're here in London, you launch a session, and next week you're in Seattle, right? So in London, at the end of your session, the object is written to the local cache, or rather the regional cache, and the object is also written to the source of truth, the origin in the cloud. When you travel to Seattle and launch your session, that object in London is really of no use because it's so far away, and that would defeat the purpose for the latency side of this. And so it'll just pull from the origin again and then invalidate the object over in London. So that's the global scale of things. Let's talk about the impact, measurable impact. So we ran a live canary across 3 regions, which represented just a small fraction of our total estate. And so with about 400,000 samples over a period of 2 weeks, we confirmed our thesis that faster uploads and faster downloads brought us some serious wins in terms of the user experience and in terms of our system capacity and efficiency. So specifically, we saw download throughput increased by about 51%, which materialized as a concrete 35% reduction in the download transfer time. So that translates to happier users, waiting less time to resume their next session. Sounds like kind of a small thing. You'd be surprised how a few seconds make a big difference. Regarding cost, this is kind of interesting. I don't have a slide on the cost side of things, but given what we know about our existing cloud provider egress usage patterns, and the observed cache hit ratios in this particular canary, we anticipate reducing the egress by hundreds of petabytes per year, and I'll let you do the math on that in terms of what that might cost. So we expected most of the performance gains here to be on the download side. That was by design. That's what we needed. And on the upload side, the average throughput from the client side saw some performance improvements as well. Some of that was expected. Some of it was a bit of a surprise. So we saw an increase in that speed on average by 45%. Again, that's from the client to the cache. But since this is a write-through cache, the upload transfer time improvements in the end are pretty nominal. And again, that's kind of how we would expect it to be. Given the nature of a write-through cache is to make sure that the data is written on the back end to ensure consistency, that kind of limits the opportunity for overall upload performance gains. But still, we saw some wins. I actually was quite pleased to see that we didn't add latency by putting a cache in the middle of that upload. And so we did some analysis. We've still got some more work to do, but essentially this comes down to the way the cache is able to use keep-alive connections to reuse TCP connections as opposed to each individual client's multi-part uploads having individual TCP sessions. So that translates into about a 5% gain on average. The P99s and the P90s are pretty supportive of this as well. I will note that depending on the object size, as you can imagine, the overhead is a bit different. So if you're talking about a 100 kilobyte object, the overhead might not have been as beneficial. Luckily for us, we're talking megabytes and gigabytes of individual object sizes. So those things were positively impacted. Okay. So when we started this, we imagined a lot of different ways to achieve it. Right? There's a whole bunch of different object storage projects out there. MinIO had been something I'd been tracking for some time, and I think it's still a pretty prominent way to do object storage in Kubernetes. For us, in this particular use case, the gateway mode that MinIO had, I think, was deprecated, and so we kind of shifted gears to a different direction. MinIO is great for other things, I'm sure. Another scenario that we envisioned, in fact, we had a small POC on this, is with Nginx and a custom Luau plugin with the OpenResty framework. It felt a little bit awkward to do that as a write-through cache through Nginx, but it's entirely possible. In fact, I've seen some other examples of folks doing that as a POC. So Nubal is quite intriguing, actually, to me. I think it's one of the up-and-coming ways to handle object storage in the OpenShift world. From my understanding, it has a lot of different backends it can support. But looking at it, there was enough system resource need and enough dependency complexity that it didn't feel like the right fit for this particular case. Remember, we're not adding control plane nodes, we're not adding hardware, we're squeezing more into the existing systems. And so that weighed a lot into how we chose our core product here. Other things, Ceph Redis Gateway, Ceph, OpenStack Swift. I think if an environment already has these deployed, I think there are scenarios where perhaps a cache such as this could be implemented. So AIStore really shined for us for a few reasons. My direct team was already familiar with the code base. And the team is primarily Go developers. As I mentioned, AIStore was written from scratch in Go as an S3-like implementation. The control plane is pretty minimal and fairly shrink-wrapped, and it already has the write-through cache feature that we needed. And so really what we were left to do is integrate our authentication and authorization systems, and we're off to caching systems. So again, your own requirements might lead you down a different path. This is the beauty of open source, and it's all good. So, this is the end. We're down to just a couple of minutes. I've left a link. I think it will show up on the conference page. If not, see me after this. I can send you an email with the PDF here. And again, my name is Ryan Beisner. I want to thank you for joining me. Hope you have a great event, and I'm happy to take any questions. I think we might have a couple of minutes for that.
Hey, can you hear me?
Yes, you can. Hi.
Sorry to make you wait. Yeah.
All good.
So thanks for the presentation. It's really nice.
Thank you.
Yeah, could you tell me more about so I was very interested in your usage of AIStore, right? So you said it sort of provides an S3-like background. What were the specific features you were looking for there, actually?
So we already had a client that had an S3 client implementation. It was a custom implementation against S3 endpoints. And so really the ability to do some of the basics, S3 puts, S3 gets, being able to do head requests, check on object signatures, dates, last modification, all the sort of fundamental things that you would want to know to determine if that object is newer than the one over there, right? To know which one to use. So I think the AIStore product implemented just enough of the S3 protocol, the S3 API compatibility to be able to do all of that. Plus, like I mentioned, a whole bunch of other things that are more data science related.
Yeah, exactly, because that's what I was really wondering. You said maybe AIStore has a different audience that kind of has focus on using it for those machine learning workloads.
Indeed.
So you said you wanted to focus on just the features that kind of made sense for your use case. So is that all very regional to just that cluster then? So each of the edge clusters have their own AIStore running?
Indeed. So we've got, let's say 100 cluster or 100 sites perhaps worldwide. Each of these have about 1,000 nodes in them. And so that's a lot of GPUs. That's a lot of clients, a lot of worker nodes. And yeah, so each of, maybe it'd be best to go back to the slide, but I'm going to leave it here because I think we're nearly out of time. But essentially, in the picture that I showed with the 4 clusters, only one of them had the AIStore cluster present. And really what we were doing there is, making it a very contained environment. There would be ways you could spread storage nodes across the 4 clusters. But it was, in terms of cost benefit, in terms of the engineering complexity, we decided to stick with a single cluster hosting that, and again, within a pre-existing cluster. If our use case was more sensitive to availability and durability, in other words, not just an opportunistic cache, I probably would have gone for more of a distributed deployment. So hopefully that helps you clarify.
Yeah, thanks. It's nice to know that Kubernetes is powering GeForce. Cheers.
Fun times, thanks. All right, thanks everyone.
Thank you. Thank you, Ryan.